What's going on? Are you able to see things or?
Okay, yeah, just now I started being able to see the slide.
Okay. Yeah, it's kind of interesting. It asked me to install the app, and then when I said I'm going through the app already, and then it said it's already showing it, then I had to switch to the window. And so anyway, let's. Um, all right, so welcome everybody, and I guess we'll continue our discussion about the dependence analysis and loop transformations. And we'll try to get to the dependence analysis part of it as far as the loops are concerned. And we were looking at some concepts last time. So when we were almost our lecture, so I'll kind of revisit some. And then from there, we will continue. So main concept here we were looking at was the idea of iteration vector of a particular iteration of a loop. So as you know, a loop nest typically is a nested sequence of loops. In this particular example, there are n nested loops, one inside the other. And what we have here is the iteration vector. And I1 corresponds to a particular iteration of the outermost loop. I2 corresponds to the particular iteration of an inner loop, second loop, and IN is the innermost loop's specific iteration. So if you take the specific iteration, form a vector out of those, that's your iteration vector. And we designate here is by I. So as you know, the loop executes as given by the semantics, sequential semantics, outermost loop executing and then going into inner loop and so on. And so it generates different iteration vectors during the execution, and the set of all this is called as the iteration space. So we are looking at this example, which is fairly easy to understand. What is the iteration space that is generated by this particular loop nest, if that's the question that is asked. So what we had to do for doing that is find the sequence of the iteration vectors by following the loop semantics from outermost to the innermost, and generate a set of those, and that's the iteration space. So if you do that for this example, you can see that the outer loop I and inner loop J execute in a particular way. The first outer loop I is equal to 1, and immediately it goes into the inner loop, inner loop J. J is equal to 1. And so 1, 1 is the iteration vector that is generated here. Next, the J loop tries to increment because of the innermost loop. But in this case, it is upper bounded by I. So it cannot go to the J equal to 2 value for the current I equal to 1 value. So because of that reason, inner loop terminates. Then we go back to the outer loop in this case, and I will be equal to 2. And again, the J loop will be entered at J equal to 1. So 2, 1 will be the next iteration vector that will be spanned here. And after that, J will again increment from 1 to 2. In this case, I is equal to 2, so J is allowed to go up to I. So the next iteration vector that will be generated is I equal to 2 and J equal to 2, which is 2, 2. Again, at this point, inner loop terminates. We go back to the outer loop, and that executes I equal to 3. And in this particular case, the inner loop is entered again as j equal to 1, and goes from 1 to 3, and that completes the inner loop, and that also completes the outer loop. And so this is the set of these vectors is basically a iteration space. As you can see, it is traversed in a particular manner. It goes from 1 1 to 2 1, and then from there it goes to 2 2, and then from there it goes to 3 1, 3 2, and 3 3. So now, what is the implication of this? The iteration space, an iteration space vector or iteration vector. So as this iteration space is traversed in a particular manner from one vector to the other, given by the loop semantics, during each of the iteration vectors, this also generates, this executes the loop body and generates the R value and L value references out of the arrays. So for example, when we are at the iteration vector 2, 1, you can see that the value, the R value that is accessed here will be 1, 2, A of 1, 2, and it is assigned to L value 2, 1. So this means that what we are doing is some reads and writes on the array references which are referenced within the respective iteration vectors. Now, one exercise one can do for determining if there's a dependence or not is to enumerate, of course, the iteration space like the way we did it here. And at each iteration vector point, find out the R values and L values in the array space or spaces which are generated, and then generate a trace of those, and that will be our read-write references which are generated in each of the iteration vectors. And we'll do this for the whole of iteration space. That means for each iteration vector, we'll go inside, we'll enumerate the reads and the writes, and we'll keep doing this for all iteration vectors and generate a sequence of all these different reference points in the data space. And then using that, find out that, hey, this particular data item, let's say A of 1, 2, was read here, and maybe in a little later iteration it was written, and things like that. So that will determine the read-write order on specific array references, and using that we can find out if there is a dependence or not. Of course, this is the fully enumerative way of doing this, and of course, if the loops are very large and they have large number of iterations, and they also have lots and lots of array references inside them and complex ones, this can take forever, and of course that's not going to work. So in order to determine the dependencies, we'll devise different techniques which will take the iteration space and which will try to project it onto the data space, which is the array references, and find out if there is a dependence or not. And that's basically the main topic of dependence analysis we're going to look later today. So important thing here about all these dependencies and the relationships to the iteration vector is that the order in which they occur, as I was mentioning. And you can see that In the previous slides, we had enumerated that order. And in general, um, what we can do is we can put an ordering on the two vectors, which will occur before what in a normalized space of the iterations. And this is very easy to understand. This is based on all the way the loops execute. So let's consider the two iteration vectors which have I and j, and we can see that the ordering of those in terms of which occurs before what is I is less than j, let's say, is decided because of one of the two occurrings here. One is the vector itself, I through n minus 1, is less than j, 1 through n minus 1. So in other words, whatever is the instance of I there occurs before the instance of j. That is one possibility. Or it's such that we have all these different instances in their components. They are all equal, but the last component of I, which is in, occurs before j, which is jn. So that's very easy to see that I'll just use the white board here to just quickly illustrate that. Okay, so let's see how that is the case. This is a little bit more formal way of stating it, but basically this is how really it is going to work out, and that should be very easy to see. So we have, let's say, different loops here, I, j, k, and they are all normalized. Let's assume that 1 to n, 1 to m, and 1 to p. Now you can see that there could be two iteration vectors here. Let's call them as I1, J1, and K1, and I2, J2, K2. And we want to determine the ordering of which occurs before what. Okay, so we want to establish if this is the case. If this occurs, the first one occurs before the second one, this is true provided I1 is less than I2. That's one possibility when this is true. But that's not the only one. The other possibility is this, that, so the outermost, so first let's write these possibilities and then we'll explain it. They're very easy to see, as you will clearly see here. Or I1 is equal to I2 and K1 is less than K2. So what it is showing is, as you can imagine, this I iteration space is first traversed in a particular way, 1 through n, right? So if the iteration vector I1 has a component, the first component, which is corresponding to the outermost loop, is less than I2, then obviously I1 iteration occurs 2. And regardless of whatever occurs inside, you can see that in the overall iteration space, this iteration vector would occur before that iteration vector, because you would see that the I loop will go from 1 to I1 first, then execute for all the inside values of j and k, and then it goes from there further and then executes at I2 for all the different values of j and k inside. And so regardless of j and k vector values, maybe this j1 is greater than j2 and k1 is greater than k2, it doesn't matter because the outer loop decides the execution order, and I1 is less than I2. We are going to get this particular iteration vector ordering like this. So this is one way I1, J1, K1 is less than I2, J2, K2. The other possibility is, however, this, that I1 and I2 components are equal. So let's say we are within a given iteration of I loop. Here, let's say that I1, which is also same as I2. And within that given iteration, what we are doing is we are hitting the J loops iterations. J1 is less than J2. And so therefore, again, that iteration is, this iteration is occurring before the other one. By a very similar reasoning, because the J loop will execute, given I loop being held constant, the J loop will execute J1 before J2 in a normalized sense. Which means that this is increasing order of execution and stride 1. And so because of that reason, I1, J1, K1 is ordered before I2, J2, K2. The third possibility is, of course, I1 and J1. They are both held, they are in the same loop iteration space. I1 is equal to I2, J1 is equal to J2. And obviously now the inner loop decides which iteration occurs before what. So if K1 is less than K2, then obviously this is the iteration vector order. So why is this important? This is important because that kind of decides which is the iteration which occurs before what. And let's say during this particular iteration, why is this order important? This order is really important because it tells us that if there is a dependence which is from given iteration vector to another iteration vector, then what kind of dependence is that? Okay, so for that matter, let's quickly look at the dependence aspect of this. So this aspect, what I have mentioned here, is purely about the iteration spaces. But there is obviously a dependence aspect of this. So if this is clear why this is the order, then we can look at um, dependence aspect of it and how to kind of incorporate that as in terms of what we are looking at. So, so what I'm going to do now is do a similar kind of a loop here. This is my I, this is my J, and this is my K. And again, I'm going to say that I have I1, J1, and K1, and I2, J2, K2. Now inside the body of this, I'm going to have two references. And I'm going to say that this particular reference here, let's say it's a three-dimensional thing corresponding to these three. And for the sake of it, I have some function of I here. Okay. Some function of j here. And some function of k here. Okay. So this is function of I. Similarly, this function of j and function of k only. And similarly over here, there are functions of I and j and k in each respective dimension. And I found out that indeed there is a dependence here between the respective dimensions of these array reference. So I can say that this particular one and then this particular one, somebody is not is muted. Can somebody who's typing can you mute, please?
Oh, sure. I'm sorry. Mine changed.
So so these two are equal. The first dimension, the second dimension is also equal, and third dimension is equal. Somehow I have found that out. How we find that out? That is going to be, of course, the topic of dependence detection. But just to tell you, f1, which is the function of I, and let's say this should be f2 of I somehow find out f1 of I is equal to f2 of I, and when this becomes I1 and this becomes I2. Okay, so function 1 of I1 is equal to function 2 of I2. I have somehow found out for these two iteration vectors. What I did was I evaluated somehow these functions. This is my first index into the loop, which is a function 1 of I. I took that, and function 1 of I1, which is this, evaluated it at this particular value of I1, and then took the this particular reference, and f2 of I was there. I evaluated it at iteration point I2, and I found them to be equal. And in a similar way, if the other functions which are in the other dimensions for f of j and f of k, they're also found to be equal for respective values. For j1 coming here, and then k1 coming here, and then I1, of course, was here. And then similarly, I2 was plugged in here for that function, J2 was plugged in, and K2 was plugged in there. So respectively, I found these functions in each dimension, and I equated them, and they were found to be equal for these values of I1, J1, K1, I2, J2, K2, which are the surrounding iteration points. I hope everybody is understanding what is going on. What we did was somehow we took two iteration vectors, I1, J1, K1, and found out the indices, the array index expressions for this A in taking each of these dimensions. So something like, for example, this, the function of function 1 of I could be 2I plus 1. That could be one kind of a function. This could be j minus 1, which could be the function of j, and this could be 3k plus 5, something like that. Okay, so these are examples of some of these functions, and in this particular case, it's L value of A. I took this I1, J1, K1 and plugged it in and got some values of each one of these functions for respective values of I1, J1, K1. Now, I took another iteration in the iteration space vector, and similarly, I plugged it into the R value side of this reference here of A, which is also the functions are not exactly the same. They could be some other functions. They need not be the same. They could be other functions here. But I did the same activity for each one of them and found out their values here for I2, J2, K2. And I found out that each one of these values that I had here and their corresponding counterparts here, they exactly are equal. So the first value is same in I dimension, in second j dimension is same, k dimension is same, which means they are basically dealing with the same array reference. Okay. So for example, they are all dealing with a 20, 30, and then say 5, something like that. Just a made up example. They are all projected to the same array point in the array space. What it means is this, that during the course of execution of this loop, um, we are writing to the same location because of this side, generating this reference here. And we are also reading from this reference because of the R value generating it. Now the question is, of course, who is doing whether it is so the dependence exists because the Bernstein conditions are satisfied that there is a read and there is a write. And if we try to parallelize these iterations, things will be problematic because we will do these read writes. We are generating them in a particular order in this loop, but in the parallel loop, the order will be indeterminate. Anything can happen before any other thing, and because of which the loop semantics will get violated. Now the question is, we are curious, of course, what kind of dependence it is. Is the read occurring before write, or is the write occurring before read, or what is going on here? That will define two different types of dependencies. So that is exactly the point which is governed by this ordering of the iteration space. So you can see here that we will have um, ijk values which are present in terms of these vectors here, right? We have found the dependence and we have these values. Now, if we have it in such a way that let's consider the different relationships which could be there. Okay, so let's say I1 is less than I2, right? This is the relationship we found on the vector when we solved these equations. We also found I1 is less than I2. What it means is this write is occurring, which is occurring at I1, is occurring before the read, which is occurring at this. So what kind of dependence is this? Anybody? I1 is less than I2, and I1, I2, I1, J1, K1 is the vector which corresponds to this one. I2, J2, K2 is the vector which corresponds to the write, to the read, and I1, J1, K1 corresponds to the write. And I1 is less than I2. So what kind of dependence we are seeing here? Is it flow or true dependence? Is it anti-dependence, or is it output dependence? We have three dependencies which we have seen as per whether the write occurs before read, or whether read occurs before write, or whether one write occurs before the other write. Any guess? Okay, maybe pretty clear here that the dependence will be governed by whether, of course, the write is occurring before the read. And in this particular case, the iteration which is responsible for write, which is I1, J1, K1, is going to occur before the iteration for the read. So the write will occur before the read, and that means that this particular dependence that we have found will be one of flow dependence or true dependence. Okay, this will be a flow dependence that will occur over here. The similar possibilities exist, as I was mentioning. If I1 is equal to I2, but J1 is less than J2, then also will be write before read kind of dependence, because the iteration I1, J1, K1, which is responsible for the write, would have occurred before the I2, J2, K2, because of the relationship we saw earlier on the dependence iteration vectors. The first relationship was I1 is less than I2. That means this iteration is ordered before this. The second one is I1 is equal to I2, but J1 is less than J2. Then also the same relationship exists. This iteration occurs before that. And then I1 is equal to I2, J1 is equal to J2. But the last one, K1 is less than K2, that also means the iteration which is responsible for write does occur before that of read. So in all three cases, we would find this is a flow dependence. The value of A, whatever reference over here, will be generated first during the execution of the program, and that value is what will be used in this read of A. So that's what it basically means as far as this vector is concerned. Now, is there a possibility that an anti-dependence exists here? And that's what we had to kind of look at in this particular execution order. When would that be the case? So you can imagine that the possibility that would lead to such a case would be something like this. Let's say I1 is equal to I2, J1 is equal to J2, but the iteration which is occurring in terms of the write, which is K1, is greater than K2. That means we are doing the this particular read first, because K2 is smaller than K1. So the possibility would be this I1 is equal, J1 is equal, and then this is greater, that is K1 is greater than K2. So what it means is the read would occur on the old value of A. The K2 will execute first, and then the K1 will execute because K1 will be, let's say, equal to 10, K2 is equal to 2, for example. So K2 would have occurred before K1 in the innermost execution. And because of that, it will be an anti-dependent thing. So this type of vector, if we find, or the relationship if we find between these different components of iteration space, and by knowing what we are looking at, whether it's a read or a write, we can actually determine whether it is a read followed by a write or a write followed by a read. And that's kind of important because, as you know, if it's a true dependence, there is hardly much we can do with it. We must sort of obey it because it actually has a data flow associated with it. The value of A that is generated in that write is the one which is actually going to get used in the subsequent read, which is going to occur after a few iterations. And so we just cannot change that particular fact. However, if it's dependence, which is something like an anti-dependence, there is a possibility that we could remove it. How can we remove the anti-dependence? So let me clear this slide and then we'll continue from there. That should be fairly easy. to see. By just renaming the output array of this appropriately to another array, we could save the new values in another array and then uh, see how we can merge this new array and old array together. It will of course cost us some operations, but maybe it will be is better to do that because then the loop can execute much faster because of parallelization. So we can remove the anti-dependencies, something like this is my read and that's my write. I can change this to another variable A1 and this could to A2, just like in SSA. And now we don't have dependence. What it means is we are saving all the new values in a new memory location. And the cost and benefit of this could be analyzed, etc. But theoretically, it is possible to remove an anti-dependence, and there are techniques to do so. And if we do that, we could parallelize this. But the first problem itself, what I'm saying is this, that we must detect a dependence, and we must find out what kind of dependence it is. And based on that, then we can do some further cost analysis, some restructuring to do parallelization and memory copies, etc., etc. So those decisions can be taken later, but we must first find out if there is a dependence. And second is what kind of dependence it is. And for that particular matter, we must analyze what we call as the iteration vector, which determines the relationship between the different components and decides whether read occurs before write, etc. Shown in this particular example. You can also see that certain kinds of orderings of execution are possible in terms of the dependencies, and certain are not, and we'll get into that a little later. But we'll try and decide what kind of dependence it is, and which is the loop which is really carrying the dependence is the real question that we will try to address next. So you can see here that the first two loops in this particular example, that's just equal to, so they are not really carrying the dependence. The one which is really carrying the dependence is, however, the innermost loop. This is the problematic one. And perhaps one can think of just parallelizing the outer two loops and leave the innermost loop non-parallel in this case. Because if we execute those iterations in order and the dependence carrying loop as non-parallelized, you can see here that we will achieve a good bit of parallelization in I and J loops. We take those iterations and we parallelize. There is no problem there. And given I and J being equals, the dependence will be satisfied internally by executing K loops sequentially within each of these processors. So that may be one way to solve this particular issue. The dependence carrying loop here happens to be this. So what in general is the dependence carrying loop is really what matters. And if we do not violate that dependence carrying loops execution order, then we are able to keep the loop semantics intact. As you can imagine here, that would be by executing case sequentially and not parallelizing that. But I and J could be parallelized, which could be pretty substantial. Any questions thus far about this? Which is really the basis of iteration space vectors, and the definition of what exactly, why are we really interested in the iteration spaces is the big question that we are trying to answer here. Again, because of the ordering of iteration spaces in the normalized manner, once we know the dependence, we know from there what kind of dependence it is and how we must preserve it. We can preserve it by maintaining everything from the dependence carrying loop nest intact by keeping that intact and by changing the relative ordering of the loop nests which are above them. That shouldn't matter, but the innermost dependence carrying loop is what we must preserve from there downwards. And that's what we'll try to do to partially take advantage of whatever is parallelizable. So if there are further questions, we can take them up anytime. But if not, and then I'll switch back to the other plots.
There's no questions on chat or anything.
Okay, good. So the ordering is really is critical, and so let's formalize whatever we have looked at into these few slides now. And so we first note that there is a dependence. If there are two iteration vectors I and j such that one of them occurs before the other, and then there is a path from S1 to S2 execution path, and S1 accesses memory location in iteration I, S2 occurs accesses memory locations in iteration j. That's the assumption here. And there is a path from S1 to S2, and I occurs before j, and then one of them is a write. So if it happens to be S1 which has a write, then that will be write before read, given I less than j, and that will be a flow dependence or a true dependence, like what we saw in the earlier examples on the whiteboard. If that happens to be, however, read in I and then in write in j, then it's a case of read occurring before write, and that's anti-dependence. And flow dependence is inevitable, but anti-dependence, we can do some restructuring, we can partially parallelize this, and so on. Regardless of whether we restructure or not, if there is some dependence carrying nesting level k, can always parallelize above it because it doesn't change the execution order in that space. But below it, we must maintain the original order because if we change that, then we'll get messed up. So that's the way to use the dependence equations, the information. So let's look at it. This first, how we can find this dependence, if it's there or not. That's the most basic fundamental question. And then perhaps worry about the execution order. So going back to this example, which we are looking at in the terms of the iteration spaces, and then we can see here that what we could do is find out what is going on in the array space in terms of these 1, 1, 2, 1, 2, 2, 3, 1, 3, 2, 3, 3. So and find out the read writes, and we want to find out if there is any dependence here which is generated between the two iteration vectors I and j. So where do these I and j come from? Of course, they come from the iteration space, which is enumerated here for this simple example. In general, that will not be enumerated because that will be like few trillion times we'll be enumerating these vectors, and That will not be the way to solve this problem, but just this is for illustration. So we enumerated it 1 1 2 1 2 2 3 1 like that in the as we talked earlier by visiting the different points in the iteration space in the order. It's also in a proper order here. Next, what we'll do is we'll take each one of these iteration vectors and we'll find out if it's read-write sets. Okay, so 1 1 means you can see that A11 will be accessed first and A11 will be accessed next. Now you will suddenly say, oh, this is there's no dependency here. There you're accessing the same element here. But note that what we are really interested in here is not the dependence within the same iteration across two statements. There might be such dependencies, and there are such dependencies many times. But our unit of parallelization here is two different iterations. So we are looking at I and j when I is not equal to j here, okay, in particular. So not when we are talking about the same iteration, because we are not in, even if there is a dependence internally, that's the iteration which we are going to just give it to one processor and we are not going to parallelize. So that dependence is going to be taken care internally during the execution of that iteration. Anyway, so now let's go to 2.1 and you can see here that between the first iteration 1.1 generated A11 as read-write sets, but 2.1 will generate 1.2 as one of the read sets on the right hand side, and 2.1 will be the write sets. So obviously for this particular iteration there is no intra-iteration dependence also. And there is certainly no inter-iteration dependence because 1.1 is different than 2.1. So you can imagine here that if you continue in this particular manner, take the third iteration, there will be a 2 read, 2 write. So there is an intra-iteration dependence, but again, there is no inter-iteration dependence because you will see that they are very different in terms of their read-write sets. And continuing so on and so forth, you will see that occasionally when I and j are equal, you will have an intra-iteration dependence, which is not of interest to us, but a cross-iteration or loop carried dependence, what we call is by loop carried, which means that a particular iteration is carrying that across the execution for these two different instances. So you will see that such a case does not exist in this particular case between two different j iterations, two different I iterations, and so on of these different iteration vectors. And therefore, this particular loop is indeed parallelizable, as you can imagine here. So you can see here that this loop is, in some sense, j of I is folding this on I of j, making it it's folding a triangular loop onto the other side of it, and so there's no dependence because the write is going on the other side of the triangle in the matrix space, and the read is occurring on one side of the triangle. So that's why there's no read-write conflict here, and it is free from any kind of dependence here. Any questions about this? So this could be a very brute force kind of way of generating these things. and then checking and so on. And it, of course, is not the way things will be done in practice. But at any point, if we had found indeed that, oh, there was a conflict in the read-write set, we would have resorted to the dependence direction vector in this case, which is lesser than what, and then whether the read occurred before write or write occurred before read, we would have determined using that. And that way we would have known that whether this is an anti-dependence, um, which is read before write, or whether it is um, uh, flow dependence. So now, having understood this notion of really what a dependence means, and the ordering of these vectors and so on, let us see what I was mentioning earlier, and the role of dependencies in terms of reordering transforms, and how does that work. And then we'll look at the how to actually find the dependencies themselves. So what are we going to do with this information of dependencies and reorganize what is really the question. And as I have been mentioning, we are really interested in finding out the iteration space vector relationship to this dependence and what kind of dependence it is. And what can we change in this loop nest given this particular dependence. So in other words, we have a k-nested loop. We have found out that maybe there is a loop carried dependence in particular depth in this loop. Let's say we have a 7 nested loop, and level 5 there is of the loop there is a certain kind of dependence, flow or anti or whatever, and using this information, can we do some parallelization? Obviously, the whole of the loop cannot be parallelized, but what can be parallelized? What we must preserve, what we could change, that really determines the answer to this question of parallelization. So in general, parallelization is one type of a transform. So reordering transform of any program changes in general the execution order of the code. Okay, originally it was doing it in a certain order, traversing the iteration space and obviously the data space correspondingly. But now if you have changed the order, it is going to traverse the iteration space in a different way. If you have parallelized it, we won't know the order. That is also equivalent to saying that it could do it in any order. Okay, and so on. So this transformed way of traversing the space and underlying data space, is there any sort of violation of the program semantics because it changes the read-write sets? As simple as that. Something which is read before and written later is basically an anti-dependence, but now you suddenly change the order and you did the write first and you did the read later. So whatever was in fact reading old values, you changed to reading new values which are generated in the loop, and that's a semantic violation. So that is what we are after. And in this particular process, we are also making sure that we are not really adding or deleting any statement in the program. We're just changing the order of whatever is there. So the key of this is reordering transformation preserves the dependence if it preserves the relative execution of the source and sink of that dependence. That is the key. If we change it as I have been mentioning, then obviously it will be wrong. And then obviously, if we preserve the dependence order, then we preserve the original semantics of the program. So finally, the valid transformations on the program really depends on whether they preserve all the dependencies or not. And that's kind of illustrated in this two simple examples, one valid and one invalid. So let's go through those, understand those, and from there we'll see how to sort of formalize some of these statements in terms of the exhibition of the dependencies and the kind of transformations that we are allowed to make on the programs. Any questions so far about the overall idea? So this is headed in a little bit into linear algebra and other things which you might have studied long back during your CS undergraduation and forgotten. Not to worry, we are not going to use heavy-duty linear algebra here. It is possible to do so, but that's left for the advanced classes in this area. And you will learn it if you do parallelizing compilers or polyhedral analysis and all these related concepts which develop these ideas more. So, but here we'll simply focus on the important necessary concepts here at a very basic level without the polyhedral analysis or without the resorting it into a theory of linear algebra. Okay. Any questions? No questions. Let's move further. So again, we'll try to keep this simple. We have a do loop 1, 2, 3, and we have two statements. You can see that they are referencing A as a write set, B as the read set on the first one, and the reverse on the second one. B as the write set and A as the read set in the second case. Now, what we try to do here is you can see that in one case we have on the left hand side, let's analyze the dependencies and let us see what we have done, whether it is right or not. And then on the right hand side, we have changed the iteration space traversal. And because of that, the relative order in which things are going to be visited is going to be different. And that will lead to either problems or will be the same if there are no dependencies. So, so you can see, first of all, we have a simple iteration space here increasing from 1 to 3. And let us see what the dependencies are here. So if you focus on the A references, A I plus 1 and A of I, you can see here that the solution to those would be that the I1 iteration, I1 plus 1 is equal to I2. So in other words, the write iteration, the one which causes the write, occurs before the read. Okay. So I1 occurs before the I2. And in the B space also, as far as B is concerned, B of I plus 1 and B of I. So let's again do the same analysis for B. The I1, which is doing the write into some B, is always one less than I2. which is doing the read. So this is also a flow dependence, which is occurring from I1 less than I2. So both are occurring I1 less than I2 um, types of dependencies. So as long as we do not mess around with the relative orders of these dependencies, we are free to um, um, change the statements within an iteration. So whether we do this A plus S1 first or whether we do S2 first, that really doesn't matter because they're not really loop independent iterations. You can see they're carried by the loop, and if that particular dependence in S1 which goes to S2 from I1 to I2 goes across, where I2 anyway occurs only after I1 is over. So if we push it, for example, S1 at the end of and S2 at the beginning of I2, it shouldn't matter, and that's exactly why the relative orders remain the same. Within an I1, the order is different. Within an I2, the order is different, but across I1 and I2, as far as whether things occur, things occur in I2 and I1 occurring before I2 is concerned, it is valid, and that's why the left-hand side transformation is a valid one. Okay, because it maintains the relative orders where they really matter. In this example, if we had a dependence, for example, this is where I think the in-person teaching really helps a lot, but I will do my best to show it. I wish there was a way to show both of these side by side. At least I don't know of how. So let me. I had to stop and then. Okay, so if I had a loop, and if I had S1 here and S2 there, and I showed you that the dependence of S1, and I'll just write it here. So we have a dependence like this from I1 to I2, and I1 is less than I2. That's the dependence I showed you in the example previously. And we switched this I1, I2, S1, S2 here. So, but the dependence remained contact because it got shifted to instead of starting at the beginning of the I1, when this one was S1 here and this one was S2 there, it started at the end and terminated at the beginning. But the dependence was preserved because it was again across the I1, I2, and we did not really affect it. In this example, we did not have a intra-loop dependence like this. If we had it, then we can't really switch things around in terms of interchanging S1 and S2. So for example, if we had A of I, and this is A of I2 here. Now you can clearly see that the dependence here is within an iteration, not across iteration. And if we switch the order, first within an iteration, what was happening? It was write, then followed by read. That was the original order, but if we had switched it, then the read will occur before the write, and that will be wrong. Okay. So whatever is shown here is valid because of the cross iteration dependence and because of the fact that we are are not violating it by swapping the statement order. So I hope that is clear for this particular example. And it's a loop carry dependence, remember that. And we will now show that that can be violated by the order of traversal of the iteration space. Here we did not change the order of traversal. We simply switched S1 and S2 order. Again, there was no intra-iteration dependence. This was not there. It was only inter-iteration dependence like this. And by switching these statements around, instead of starting at the beginning of I1 and ending it at the end of I2, it started at the end of I1 and ended at the beginning of I2. And that's how the dependence was still maintained across iterations, and therefore there was no problem here. Any questions? Okay, now back to our other example. And let us look at the right-hand side example now. Now, if you carefully see it, instead of going from 1 to 3, I'm going from 3 down to 1 in a different order. I start at iteration 3, then I go to 2, then I go to 1. So the order of traversal of the iteration space is reversed. And I keep, of course, the execution order S1, S2 as the same. But because of this reason, now you can see the changes that occur. So originally, the dependencies that were there in the top loop were writes followed by the reads. Got it? So we were doing, for example, for I equal to 1, write of A equal to 2, and for I equal to 2, we were doing the read from A equal to 2. So writes were occurring before, and then following those, reads were occurring, leading to a flow dependence. Now here, see what happens. Iteration number 3 is followed by iteration number 2 in this particular case. So what kind of read-write situation exists here? You can see that the situation is reversed here. The read-write order is messed up. So as far as A is concerned, and similarly as far as B is concerned, you can see that in a iteration 3, we are reading B3, and in iteration 2, which occurs after, we are writing into B. So the read is occurring before the write, and because of which the dependence is changed from a flow dependence to an anti-dependence, and that violates the program semantics. And that's because, again, we had a cross iteration dependence here. If we had it only for within an iteration, we will not have any problem, because within an iteration will anyway be just fine as long as the iteration is the dependency is preserved. But that will not be the case, because this iteration is this dependence is carried across iteration, and now the iteration which is supposed to generate a write is occurring only after the iteration which is doing the read, because of the change order of the iteration space traversal. And so the iteration space traversal, if it is affected in any way, like in this, and if it doesn't preserve the dependence, then we are in violation of the dependence, and therefore it is invalid on the right hand side. Now this could be one reason for violation, that we are traversing the iteration space in a different order in a given dimension, or we have done some parallelization and things like that when they are not supposed to occur. As you can see in this particular case, even parallelization will be invalid, not just the reversal, because you can see that we are supposed to maintain certain order in the space as far as read writes are concerned. By parallelizing all three iterations, we would have potentially violated that order, and so parallelization is not allowed because of that particular reason in this case. So two different reasons. Sequentially, we have violated the order. That is one problem. By doing parallelization, we have violated the order. Another problem. And that's the reason why parallelization is not possible when we have a cross iteration dependence and so on. Now, as far as the dependencies and loop transformations are concerned, how do we go about it and what do we do? So the big thing that we must do is we must carry out, of course, first dependence testing in a viable way. We cannot carry out by using enumeration. That will mean a huge amount of compilation time. So we will do dependence testing in a very fast and efficient manner, and find out if the dependence exists or not, what kind of dependence is there, and so on, in a normalized loop form. And then use that information and carry out transformations which are dependence preserving in a given dimension. Okay, so sometimes, obviously, again, we are led to a problem here because of different reasons. The two primary sources of approximations we are forced to do is, one is because of the program characteristics. That is, even if we have most perfect dependence tests, we will not be conclusive there. We will not be able to say that the dependence for sure exists or it doesn't exist because of that problem, even in the presence of most powerful and most accurate dependence testing. But the bigger problem is that dependence testing is NP complete problem, just like any others, most of the CS problems that we encounter, and we must try to find out a conservative approximation of it, which is safe. So let us look at the inherent problem of dependence analysis even if we had most perfect dependence tests. So as you can see in this particular simple loop nest, if we have something which is unknown at compile time, then what are we going to do? You can see that A, K, I plus 1 and AI plus BI. So in this particular case, if K is equal to 0, obviously there is only intra iteration dependence. But the moment K assumes any positive or negative values, it becomes inter-iteration dependence and doesn't allow parallelization. So only when K is equal to 0, we can parallelize the iterations. In other cases, we cannot. In one case, it will become a flow dependence. In another case, it will become an anti-dependence, but in either case, prevents parallelization. So we must then assume K is conservative and there is a dependence and give up parallelization. Or in this particular case, K is a loop invariant, it's not changing, and we can test the value of K at the entry point of the loop and invoke a parallel version if K is 0 and all other versions will be sequential. So one other definition which follows from what we looked at earlier is what we call as a dependence distance. We looked at a dependence direction vector, which is the relationship between the respective dimensions of the vector space. But the distance is simple. So j minus I, that value, whenever there is a dependence, the relative difference between the two iterations is basically the dependence distance. And the vector representation of this um, um, is basically a distance vector. So looking at this simple example on the left hand lower side, a of I plus 1j and a of ij. If we analyze the dependencies here, you can see that the respective vectors for which the dependence exists, you can see that if I were is equal to 1 and j is equal to 1, then you can see for 1, 1, iteration vector, the corresponding vector there will be on the read side will be 2, 1. So this is a true dependence because obviously for a lower value of I, here we are hitting the rights of A and then following that in the next iterations of I, we're reading those, and the dependence is carried by the I loop here. But if you look at the respective differences between the I and j components of the vector, that is 1, 0. So you can see that this is the dependence distance, and it is basically 1, 0. So that means in the I outer dimension it is 1 and inner dimension it is 0. And obviously there is a use of this information at some point in terms of finding out how much apart is the generation of A versus the consumption of that same value, whether it is going in the innermost loop or whether it is in the outermost loop, things like that. And one can then use this information to carry out some transformations. Just a quick note here, as far as this loop is concerned, the distance is 1, 0. In the outer dimension it's 1, inner dimension is 0. So somehow if we are able to interchange this I and j loop, how do we do that? That's a separate issue. And bring I loop as inner loop, you can see that the number of iterations that will elapse between generation of A in the write versus its consumption in the read will be just one iteration apart. And having this one iteration apart inner loop between the generation and consumption, what we can do is we can keep this value in a register and therefore take advantage of the true data, and we can save memory accesses there. If we do it the way currently it is, it will be a huge problem, because if you look at it, the write will originate at whatever I value, and will get consumed at whatever is the I value in the next iteration. But intervening the two I values will be a huge number of J values, and so the register will have to be kept busy for so many J values, and there will be a big problem because of that. So this is how the information will be used in terms of facilitating some other transformations. Further on, many times this dependence distance is not fixed as what we have shown, but we only know whether it is positive or negative and so on by looking at the respective references in the array space. And this is what we call as dependence direction vector less than, equal to, greater than. And again, that is being used, that is typically used transforms to perform the changes by determining the kind of dependence it is. So we had looked at it earlier in terms of out whether this was an anti-dependence or a flow dependence, and then trying to do some changes based on that and so on. So that's where this information is useful. So here is an example of some of these, which is dependence distances that are there just for the same example that we had already seen. Then dependence direction vector, which is between I1, the respective components of I and j here. So 1 is less than 2, so we have strictly less than their first component. The second component is there both equal, so things like that. The other things that is done typically is once we know these dependence direction vectors and we form a graph here between different statements and represent the relations. We of course don't form a dynamic graph, but just a static one. In other words, each statement represents all instances on the execution of S1, and S2 does the same. And we find out if we can represent the common relationship across all S1s to S2s. And that's what is shown here. Typically, this relation is ship in this case is you can see that A of I and A of I is equal in terms of flow dependence there within the intra iteration. And then, however, the dependence between S2 onto itself is one of, again, flow dependence from S2 to another instance of S2, of course, in the next iteration. But the origination here is right followed by the read. And so this is a less than dependence which is being shown there. And so this is shown in terms of data dependence graph. And then using this graph, we'll see once we finish the discussion of dependencies, how to leverage the graph and do certain transformations and so on. So for example, we can keep the dependency intact and sometimes maybe cut a loop or we can even merge another loop and preserve the dependencies, and that might help us in terms of locality and so on. So loop independent dependencies. Again, similarly, we have this definition and all these dependencies are present only within the iteration, as we have seen earlier in some examples. Loop carried dependence, which is the most important one, which we also looked at, more formal definition here. Here is it is carried from S1 to S2, and if it is forward, if S2 occurs after S1 in the loop body, in the lexical sense, and we have this two iterations and the dependence distance is greater than 0 or the dependence direction vector has less than as its leftmost non-equal to component, and some other details here. Level of loop carried distance is the index of leftmost non-equal to part of the dependence, which basically means that dependence is being carried by the particular level of loop nest. Again, as we saw some examples, that is going to be true in this particular case. we can see here that both are loop carry dependencies from S1 to S2 and from S2 back to S1 because of F. The first one is because of A, and this is forward from S1 to S2, and the other one is backward. And you can see there all this level at less than, because obviously we have only one loop nest here, and that is the outermost loop which is carrying the dependence. But very well, imagine that maybe there is a J loop which is surrounding this, and in that case, this dependence will be carried by the inner loop, which will be the second level of loopness. So another example here. So they're all loop carry dependencies here in terms of level 3. You can see that equal to for the outside two dimensions, and less than because of the k dimension, which is write occurring before read. And you can see that we can represent them from S1 to itself by equal to less than, or by delta 3 S1. And you can see that again in this particular case, since the dependence preservation must occur, we could parallelize I and J loops here. And they're not the ones which are carrying. And within each processor will execute K loop sequentially, which is going to generate for a fixed value of I and J, which it gets all the K values and pushes them on from the to fulfill the dependence in a true or the flow sense. Okay, so in short, the dependence carrying loop nest and its level is very, very important. It's did not have my, so I think we are almost far into the end of the lecture today. I did not have my clock here. So I guess we'll stop here for now, and we will continue then in the next lecture. From here, what we have to look at is the dependence testing and the how this really is carried out by introducing minimal amount of approximations, and that's the topic, which is a very interesting topic. There had been a lot of debate on whether there is a room for more detailed dependence testing, and then later on it was shown that there really isn't one. So all these kinds of things, we'll take a look at it in the next lecture. But if you have any questions, do come by, and see you next week. Otherwise, have a good rest of the week.